Hey guys, welcome back. This is lesson 2.6 about limits and continuity. So let's get cooking talking about these topics. So first, definition of continuity. So a function is said to be continuous at a point if the limit is the same as the value of the function. So in order for the function to be continuous, these two values, limit as x approaches c of f of x, must be equal to f of c. So we're just going to take a look at this little graph over here and determine if the function is continuous at each value. So this one is kind of given away down here. So first, let's look at 0. The function has one-sided continuity at x equals 0 because the interval of the function ends. There is no function before that, but the right-hand limit exists and is defined and is equal to the value of f of c. So that is one-sided continuity. So typically when we're trying to prove continuity, we're trying to prove full continuity, so whether or not a function is continuous. So for the rest of these, we're just going to look at whether the function is actually continuous. So let's look at x equals 1. So at x equals 1, this function is clearly not continuous because the limit from the left and right are different, so the limit doesn't exist. So it can't be equal to f of c because it doesn't exist. At x equals 2, I notice the left and right hand limits seem to be equal to 1, but the value of the function is equal to 2. So it is not continuous at x equals 2. At x equals 3, the left and right hand limits both seem to be 2, and the value of the function is also 2. So the function is continuous at that point. And then at x equals 4, I notice the value of the function is not even defined at that point. So regardless of what the limit is, this is not continuous because f of c is undefined at that point. So no matter what, the limit cannot be equal to it. So it is not continuous. So if you're ever trying to prove continuity, if a problem says prove that the function is continuous at this point, what it means is prove that the limit is equal to the value of the function. So here's an example of that. This is asking, is the function continuous at x equals -3? So in order for this function to be continuous, the limit as x approaches 3 as f of x must equal f of -3. F of -3 is easy. Based on this function, f of -3 is 1/8. So I want to prove that this limit is also equal to 1/8. So in order to do that, if I can prove the limit of this as x approaches -3 is equal to 1/8, then the function must be continuous. So because this function is defined everywhere except at x equals -3, so if the limit of this as x approaches -3 is equal to 1/8, then this function is going to be continuous at this point. So let's look at the limit as x approaches -3 of the square root of x plus 19 minus 4 over x plus 3. So I'm going to try and simplify this. I'm going to disregard the limit for a second. I'm going to try to simplify this using the conjugate method. So conjugate method here. The reason I'm doing that is I see I have a radical. And sorry, first thing I should try is direct substitution. I know that doesn't work because -3 plus 3 is 0. So now I move on to the conjugate method because I see this radical up here that I want to try to get rid of. So this is square root of x plus 19 plus 4 over square root of x plus 19 plus 4. So again, conjugate method, the purpose of it is this first term squared minus second term squared. So now this is x plus 19 minus 16 over x plus 3 times square root of x plus 19 plus 4. So what I notice here is that this x plus 19 minus 16 is now x plus 3 when I simplify over x plus 3 times the square root of x plus 19 plus 4. So I can now simplify this even further because x plus 3 divided by x plus 3 is 1. So now I'm really looking at the limit as x approaches -3 of 1 over the square root of x plus 19 plus 4, which I can now do because when I plug in -3 down here, I don't get 0 anymore. So this is 16. The square root of 16 is 4. We're going to assume that we're going with the positive square root. So that's 4 plus 4, which is 1/8. So the limit as x approaches -3 of f of x equals 1/8. So the limit is equal to the value of the function. Therefore, the function is continuous. So if a problem asks you to prove continuity, that's what it's asking you to do. It's asking you to prove that the limit of the function is equal to the value of the function. The other thing that this tells me is if I were to graph this piecewise function, basically what happens is this function is defined, but it is not defined when x equals -3, so there would be a hole in the graph. What this piecewise function does is it plugs the hole in the graph using this value 1/8. So it says when I get to this value of x equals -3, I'm going to plug the hole by letting the function equal 1/8, which is what the limit would be equal to at that point anyway. So here are the different types of discontinuities. So the first one we actually just talked about. A point discontinuity is a removable discontinuity. It's when there's just a hole in the graph, but the graph keeps going. We refer to it as removable kind of because of this piecewise thing. I could plug the hole using a specific value in a piecewise function. But for the function itself, if it has a hole in it, it has a point discontinuity. Infinite discontinuities, we've talked about, these limits don't exist because they're asymptotes. The function goes either positive or negative infinity. So this is an infinite discontinuity. And then we also have talked about jump discontinuities. So what jump discontinuities look like is the left and right hand limits of the function are different. So there's a gap in the function. So now I want to look at this function. I want to give all x values for which the function is discontinuous and classify each as jump, as one of these three, as either jump, infinite, or point. So in order to figure out what causes discontinuities here is I want to look at the denominator specifically. I want to look at the denominator because when the denominator is equal to 0 is when I have issues. So I need to review how to factor. So a times c, -18. I need two things multiplied, -18, add up to -3. So this is 9x squared minus 6x plus 3x minus 2 over, again, multiply. 3 times 4 is 12, and two things multiplied 12 and out to 13. Those are 12 and 1. So I've got 3x squared plus 12x plus x plus 4. I know that some of you guys can probably factor it without doing this process, and if you can, that is perfectly fantastic. I'm just doing this to help give you a quick review of factoring. All right, so when I factor things out, I'm going to skip over a little step right here. I know that 3x minus 2 is what I'm going to be left with, so I factor out 3x. So I factor out 3x, I'm left with 3x minus 2 plus 1 times 3x minus 2. And then in the denominator, I'm going to do kind of the same thing. I'm going to factor out 3x plus 1, and I'm left with x plus 4. All right, so now in the denominator here is what is going to cause discontinuities. So x cannot be equal to -1/3 or -4. Because if I try to plug either of those numbers into the denominator, I end up getting a value that is 0, and 0 times anything is 0, so I'd end up dividing by 0. So what I notice here, though, is this factor 3x plus 1 is in both the numerator and denominator, which means this is a point discontinuity because the graph, if you remember from when you took Algebra 2, this graph does not have an asymptote at x equals -4. What will happen with this graph at this point, x equals -1/3, is there will be a hole in the graph. So this is at x equals -1/3. If I keep going further to the left, there's going to be some kind of asymptote at x equals -4 because there is no factor that is also in the denominator to take care of that factor. So there's going to be an asymptote at x equals -4. So this is an infinite discontinuity. Or unbounded is a point where the limit doesn't exist, so the function is discontinuous. So that was a quick review of what you guys did in Algebra 2. If you need any help with that, let me know. I can make a separate video about that if that's something that you would like. But for now, we're going to move on and ask any questions that you have in class. So the last point I want to make about continuous functions is if you know that two functions are continuous, then the composition of those continuous functions are also continuous. So for example, this one y equals, we can say that y equals f of g of x here. And in this case, f of x would be sine of x, and g of x would be x squared. So because both of these functions are continuous, then this function y must also be continuous because it's a composition of the two continuous functions. Same thing applies here. F of x would be absolute value of x, g of x would be cosine of x. Both of those functions are continuous, so therefore the composition of the two functions is also continuous. So that is it for today. Today we talked about the definition of continuity, how we use limits to verify continuity. So if something asks you to prove continuity, you prove that the limit is equal to the value of the function at that point. And then we also talked about the types of discontinuities. So I hope that you took some good notes. I hope that you're ready to come to class with questions. And I hope that you have a fantastic day. I'll see you later.